Your test 3 will be Monday, May the 11th. That's in line with our syllabus. There's no need for me to change. And the topic will be chapter 4, chapter 5, and section 6.1. Now, there's a chance that there's still a couple little material. Very likely 5.6 is the one that I cannot cover today, but that happens to be on the easy side. Okay, I'm pretty sure that we can cover the majority of the material today, such that we have only a little left over to do on Wednesday. Okay, so you still have a weekend to study for your test 3 though. Okay, now test 2 solution is already on your test 2 page, just like your test 1 solution on your test 1 page. So if you want to see your solution, go ahead, go to that test 2 page. Okay, let me erase that so that I don't have too much on this paper here. And then the old tests that you can study from for your test 3. Okay, I give it here. Now let's start with 5.1c. Let me finish up this section. Let me finish up this section. Now we already learned the definition of angle in radian. Definition of angle in radian is theta in radian is equals to what happened? What did I do? I rewrite it again. By definition of angle in radian, we know that angle theta in radian is equals to the arc length subtended by that angle divided by the radius. Now that's theta in radian. Now using that formula, then we can get the arc length S to be theta times R. Now just make sure that the theta okay, just make sure that the theta is in radian. Okay, that's the formula. Let me mark it. Of course, you need to memorize this too. Okay. And then for sector area, what is a sector? A sector is this region here, the pizza. That's the pizza. Okay, now the area of that sector is proportional to central angle. So the central angle theta, we will compare that with the whole circle, whose angle is 2 pi in radian, such that using that proportion to the area of the sector that you are looking for to the area of the circle. Okay, now the area of the circle is 2 pi r squared. Okay, now we play together with this. We play with this. We get the area of the sector times 2 pi. I do cross multiply. The area of the sector times 2 pi. It's actually coming from here. Is equal to angle theta times pi r squared. Okay, now then from there I divide then by 2 pi. I divide by 2 pi here. Then I get the formula for the area of the sector. Okay, so this is another formula you have to memorize. As I remember, we don't really do this, use this a lot in calculus 1, but you will use this a lot in calculus 2. Okay, you will use this a lot in calculus 2. Okay, let's do an example. Example 1. Example 1. Let theta be, let's say, 150 degrees. and the radius is, let's say, 4 inches. Okay, so we have this situation here. That's a sector whose opening, whose central angle is 150 degrees, and the radius is 4 inches. The first question, what is the arc length? The arc length refers to the length of this part here. Refers to this part here. Okay, arc length. Now, but before I work on that, pay attention to the theta. The theta here is in degrees. I need to change that to radian first. Like it has to be in radian before you use that formula. Okay, so part A, theta equals to 150 degrees. I need to convert this to radian. Multiplied by pi over 180 pi. Do you remember this? That will give us 5 pi over 6. Now, that's the radian. Then the arc length will be theta r, right? Theta r. The theta has to be in radian though. 5 pi over 6 times 4 inches. That will be 10 pi over 3 inches. Okay, so the length of that yellow arc there will be 10 pi over 3. Oh, by the way, suppose I ask the other way around, the other things like what is the perimeter? Perimeter of the sector. Well, we know this is the sector here. This is the sector, the pizza part. Okay. If you say the sector is the pizza, then the yellow part is the crust part. You see what I mean? Okay. Oops. Now, but the perimeter refers to the yellow part plus this part here. Okay, now, so the perimeter of the sector will be equals to the arc length plus twice the radius, right? This is the arc length, and this is twice the radius. Now, that will be 10 pi over 3 plus 8 inches. Okay, now how about if we need to answer the sector area. Area of the sector will be 1/2 times theta, which is 5 pi over 6 times radius squared. 16 divided by 4, that's 4, so that will be 20 pi over 3 square inches. Okay. That's for the area of the sector. Of course, we may have other type of question in which, for example, we have, instead of having the central angle, we may have something else. Let's say, let the arc length to be 10 feet, okay, and the radius equals to, let's say, what is good, 5, or maybe 2. Let's make it 2. Why? Let's make it 2 feet. And the question is, find the area of the sector. So the plan is we will need to first find the theta. After you find the theta, then you find the area of the sector. Right? Okay, let me ask you to do that in 1 or 2 minutes. Okay, the theta will be the arc length over the radius. That's 10 over 2, that's 5 radian. Usually the unit radian, I think I said this before, unit radian usually not written. Okay, either. So I can write 5 radian or simply 5. Okay, either one. Now then I will use that 5 into the formula for my area of sector area. Then there will be 1/2 times 5 times r squared. The area, oh, the area happens to be 10 also. 10 square feet. Oh, surprise. Okay, I hope that's quite simple. By the way, some little notes may be useful. Some little note. Notice that the sector area is equal to 1/2 theta r squared. Now notice that theta r is known to be s, right? This guy here is equal to s, the arc length. So I can rewrite my sector area instead of 1/2 theta r squared. I can write it as 1/2 s r. Which, if you look at the diagram, the graph, notice that it actually mimics very closely the area of a triangle, where the r is actually quote unquote the height, okay, and then the s is the base. Okay, I somehow think you can see this as quote unquote coincident. Okay, even though later on you will see that's not really the case. It has something to do with the area of a triangle. Okay, yeah. So if we know the arc length and the radius, we actually can use this formula to find the area of the sector. Okay, like suppose I use this formula, then area of the sector will be 1/2 times the arc length times the radius. Oops, 10 times 2. So you get this is 10 anyway. You see what I mean? Okay, now those two are for arc length and sector area. Now we go on to linear and angular speed. The third part is linear and angular speed. Or in West LA College textbook, they call that linear and angular velocity. Now suppose linear speed is actually in line to what we learned before. Linear speed is equal to the distance traveled, distance divided by time. Okay, now the distance that we will have here is actually the distance traveled on the circle, which is arc length. Okay, that's s over t if we use notation. So suppose this is my circle and this is my radius. Now the distance traveled, let's say it's this one here. This is the arc length. The distance traveled over a certain period of time. Okay, while angular velocity or angular speed that's actually the angle traveled divided by the time. Now in this picture here, it will be the theta. Okay, that will be the theta times angle divided by the time. Now, combining what we have, oh, the notation for linear speed. Linear speed's notation is denoted by V, and angular speed is denoted by omega. Looks like a W, but it's actually omega. It looks like W, but it's actually omega, lowercase omega. Now, if I put things together even further, actually, you need to memorize this formula. The formula you need to memorize is this guy here, oops, and this guy. Okay, so omega equals to theta over t, and then linear speed v is distance over t. Now, at the same time, we know that s is equal to theta r, right? S equals to theta r. Okay, but theta over t is omega. So linear velocity, linear speed is equals to angular velocity times the radius. Now we get another formula that we need to memorize. Okay. Now let's do problem. Let's take questions from the book. You will see this 5.1c here, the arc length, the sector area, linear speed, angular velocity. Those only memorizing formulas and ability to apply it. Just keep in mind that the theta has to be in radian. Okay, let's say for example, we take a look on number 48 in our textbook. Number 48, it's on page 333. Page 333. They give us that the radius is equal to 9 inches, and we have 2,400 RPM. 2,400 RPM. Now RPM stands for revolutions per minute. Now that implies the omega, the angular speed. Now one revolution is 2 pi radian. So this will be 2,400 times 2 pi radian per minute. By the way, you see this RPM actually on your when you drive. When you drive, that's on your dashboard. Yeah, on your dashboard you will see the next to your speed, right? And what happened? You will see the RPM, how many revolutions per minute the engine actually working on. Okay, now, but from that RPM, we change it into radian per minute. Okay, radian per minute. And then from there, that's part A. I answer part A unintentionally. And then part B will be find the linear speed in feet per minute. Okay, linear speed in feet per minute. My linear speed will be omega times r, right? That's 4,800 pi times the r. My r is 9 inches. Okay, so later on this will be in inches per minute, right? Okay, but hold on. What they want is feet per minute. How to convert inch to feet? To convert inch to feet, I will multiply by 1 foot over 12 inches. Okay. Now, I purposely didn't multiply that 4,800 by 9 because I want to steal this 48 with that 12. So this will be 400. You see? Okay. So then I get 3,600 pi feet per minute. Wow, that's really, really fast, huh? That's really, really fast. Now that's my linear velocity. Now let me ask you to do a problem. Let's say number 50. Number 50 on the same page. A typical tire for a compact car is 22 inches in diameter. Give me a second. I have some issue with this pen. So number 50, the diameter is 22 inches. So the radius will be 11 inches. And then if the car is traveling at the speed of 60 miles per hour, so the linear velocity is 60 miles per hour, and find the number of revolutions the tire makes per minute. Find number of revolutions tire make per minute. Basically, omega equals to what RPM? That's the question. Okay, we know the formula omega equals to, phi, the linear velocity equals to omega times r. This is 60 miles per hour equals to 11 inches times omega. Now we have some problem here. One of them is in miles, the other one is in inches, right? Okay, now do you know 1 mile, how many inches? 1 mile is 5,120 feet. Am I right? Or 5,180. Let me check.
Do we have to memorize that?
Hello? Yes? Hello?
Do we have to memorize that?
I think I will need to give you what is that, huh? But supposedly though, if you have, for example, SAT or GRE, they expect you to memorize this. They expect you to memorize this. But let me check. I somehow think it's 5,120, but it could be 5,280. See, I myself don't memorize it since you asked me that question. 1 mile. Yeah, 5,280. So even I memorized it incorrectly now. Eraser 5,280. 5,280 feet, and 1 foot is 12 inches. Okay, now let's convert that 60 miles per hour into inches per minute first. Okay, so we will come back to this formula later on. 60 miles per hour equals to 60 times, I need to cancel the mile, I need to cancel the hour also. So for the mile will be 5,280 feet per mile and 12 inches per feet. And then multiplied by 1 hour over 60 minutes. Now that way, that the miles cancel, the foot also cancel, okay, the hour also cancel. You see that? Okay, so now I have 5,280 times 12. My units will be inches per minute. So I'm good with my unit. So coming back to that formula, then 5,280 times 12 inch per minute is equal to 11 omega. And omega will be 5,280 times 12 over 11. That will be radian per minute. But I need revolution per minute. I need revolution per minute. I need revolution per minute. Then how do I change this to revolution per minute? 5,280 times 12 over 11 radian per minute. Now to change that to revolution per minute, one revolution is how many radian? That'll be 2 pi radian, right? That way then I can cancel the radian. So the final answer will be anything after this is calculator. The final answer will be 5,280 times 12 over 11 times 2 pi. This will be RPM. Then you can use your calculator. Let me use my calculator. 5,280 times 12 divided by 11 divided by 2 pi. I get omega will be, the angular speed will be 916.73247 RPM. Okay, so in 1 minute it's spinning as fast as 916 revolutions per minute. 917, if I round it to correctly. Okay.
Then you use in the calculator, right? Radian mode in the calculator.
Repeat again.
Radian mode in the calculator, right?
Actually, you don't need to make it into radian mode in your calculator because we don't have the sine cosine anyway. Yeah, you only need to make sure that it is in radian mode if we are dealing with the sine cosine tangent or sine cosine tangent inverses. Is it okay?
Yeah. Mm-hmm.
If you have a chance, you may want to take a look, for example, to number 55. Number 55. So it has this situation here. One of the big use why we learn this. We have, let's say, a wheel. Okay, when you ride a bicycle, and then you have the what's that? The real wheel. Give me a second. So it has this kind of situation, similar to this. So it goes this way. Now we call this sprocket here. This is call this R1. R1 is the radius of sprocket. Okay, and then R2 being the radius of this guy here. This is this one. This is R2. Sprocket 2. This radius of sprocket 1. And then we have radius of the wheel. This is R3. R3B radius of rear wheel. And we do pedaling here, right? The pedal, let's say, is here. Okay, this is the pedal. Okay, and the blue part here is the chain ring. Okay, now you will see the following. The angular velocity of the pedal will be equals to the angular velocity of the first sprocket. In other words, if you are pedaling 20 RPM, if you are pedaling at 20 RPM, then your first sprocket will be also moving at 20 RPM, right? Okay, now, however, the relationship between, this is the relationship between the pedal and first sprocket. Now, but what's the relationship between the first sprocket and the second sprocket? You will see that the linear velocity will be the same. Okay, because they have they are related by a chain ring, right? The chain. Okay, whatever the first sprocket travel, the distance the sprocket travel will be equal to the distance the second sprocket travel. Now, if I go on further, you will see that from here we will get that omega 1 R1 equals to omega 2 R2. Okay, so the larger the radius, the slower the angular velocity. Okay, now while on the third relationship between S2, the sprocket and the wheel, the rear wheel, they have the same angular velocity again. Now that's how the bicycle actually works. So that's why, for example, Louis Armstrong, one of the bicyclists, when he practiced at home, he's actually measuring the speed of his pedal, okay, the angular velocity of his pedaling, and from there he can see how fast he's actually moving by using this kind of ratio. Okay. So for him to practice, he doesn't have to actually ride the bicycle on the street. No, he can just practice at home. Okay, and put some weight on his bike, and then from there measuring his RPM of his pedaling, and the machine will give his speed. Okay, now that's for this R1C suggested homework. This section 5.1c, I'm sorry, suggested homework from this 5.1c will be number 31 to number 49. Number 49 is an interesting question though. Number 49 is an interesting question. Yeah, try to think about it. Okay. Now, when I say try to think about it, doesn't mean I will definitely ask that question. No, simply because that's something we saw in the past. Now, I think your generation, you still see CD, right? Compact disc. Yeah, you still see compact disc. Okay. Now, the thing is, how compact disc works is actually quite has a lot to do uh, with the way this RPM thingy works. You see that when you have the pin here, okay, basically the pin on the CD or the sensor on the CD on that CD will run at constant linear velocity. Okay, now you see that because it is constant linear velocity, when the radius is big, or that R1, then the phi is constant, right? So the angular velocity, if R1 is big, then the omega will be, the angular velocity will be small. Okay, so when you are actually at the pin, when you play the CD, you start from inside. Okay, you start from inside. Now, such that when you first play the song on your CD, the CD is actually spinning faster. The CD is actually spinning faster. Now, the spin actually gets slower as you go further and further away from the center. Okay, that's the idea. That's the idea. So, uh, yeah, I guess that's where I will leave you for 5.1c. Let me go on to that. This is idea for number 49. This is the idea for number 49. Okay, that's something good to see. Now let's go on to proving identities. Now in proving identities, when we prove identities, we will prove from more complicated expression to the simpler one. Okay. Now, what is an identity? Identity is basically an expression equals to an expression. Expression equals to an expression that could form an identity. When we try to prove it, either we prove from left hand side to right hand side, left to right, or right to left, depends on which we have more complicated, and we simplify that to the other side. Okay, now the structure of our proving will be as the following. This is the question. The way you prove it will be, the first line will either look like this or look like this. Now, in my test, if you write that, it will be your 1 point. Okay, now your last line will be, your last two lines will be the other side, and this. It has to be in this form. Okay, now of course I can say so many things about this here, but you don't get it. I need to do examples. I believe I did some example last time when I proved some identities, but let's do examples here. Example 1. Let's say I prove tangent theta plus cosine theta over sine theta equals to secant theta plus cotangent theta. Let's say that's what we want to prove. The first thing you need to decide is which side is simpler and which side is more complicated. It seems like the left-hand side here is more complicated. Okay, so I will prove from left to right. Okay, I will prove from left to right. Now then, on my first line, I will first show the direction of the proof, left to right. Okay, and then LHS stands for left-hand side, equals to whatever you see on the left-hand side. Don't do any computation, no any simplification, nothing to change. You need to write it as exactly as what you see on the left-hand side. Now, then when you do your proofing, the next step should be done in the next line. So you don't go to the right-hand side. You don't go to the right-hand side like this, equals to what, equals to what, equals to what. No, don't go to the right-hand side. No, 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 no. Don't do that. Okay, not like that, not like that. The next step should be done in the next line. And when we do proofing, you try to show your work in detail. So one step at a time. Don't do too many things at once. Okay, so maybe I write it down. The next step should be done in the next line. Second, one step at a time. I understand sometimes some steps are too simple that you try to skip it, but try not to skip too many steps even if you have to. Okay, make sure that's simple enough. If you wonder, can I do these two steps at once? If you ever wonder that way, then the answer is no. Okay, every time you wonder, can I combine these two steps into one step? Every time you have that question, the answer is no. Now, the third principle that we usually use is if the expression has too many functions, like sine, cosine, tangent, secant, cotangent, like in this question here. Okay, then consider not always necessary, but not always necessary, but always work. Okay, then consider converting them to sine and cosine. Okay, so like in this question here, I will rewrite my tangent as sine theta over cosine theta. And then from here, I will multiply by the LCD. That's cosine theta over cosine theta. That's the LCD, right? Then in the next step, that will look like sine theta plus cosine squared theta over sine theta cosine theta. Then from there I split it. This is equals to sine theta over sine theta cosine theta plus cosine squared theta over sine theta for sine theta. Okay, and then I can reduce the first term. That's become 1 over 4 sine theta plus 4 sine theta over sine theta. That gives me secant theta plus cotangent theta. Now notice that that's what we need on the right hand side. Right? That's what we need on the right hand side here. Right? Therefore, that's already equals to right hand side. We write in the next line, the last line right hand side equals. Now this notation here means therefore it is shown. In the past, when we didn't use computer, in the past they used the word the letters QED, which as I remember stands for Quod Erat Demonstrandum. Therefore it is shown. Okay, therefore it is shown. I remember what it stands for, therefore it is shown, but don't quote me from what this QED stands for. Okay, I think it is though, but I may be wrong. Long time not using it. Now we use this notation here since we have that kind of, we can have that kind of notation on our computer. Okay, but in the past when they use typewriter, they don't have this notation. When they have typewriter, they don't have that notation, so they use QED. Okay, so all time actually already changed since we have computer. Now, I would like you to be aware that this question that I have done here, this question that I show you here, this is example 6 on page 341. 341. On page 341, example 6. Now, if you take a look on that page, on that example, you will see the way I show the work is different from the way the textbook show the work. Okay? The way I show the work is different from the way textbook show the work. Now, what you need to adjust from the textbook, you need to show this. Our textbook does not show this. I need you to show that. Okay? And our textbook did not show this. Our textbook actually show just from here to here. That's what our textbook show. Now, so the work in between may be quite different, but the first step and the last 2 steps has to be the same. Okay. So
what does LHS and RHS stand for?
Left hand side, right hand side.
Okay. Thank you.
Sure. Okay. Now, with this said, I want to say that when it comes to proofing, proofing is not unique. Okay? It depends on how mature you are and how quote unquote sneaky you are when trying to show one thing equals to another one. But there's no unique way to show a proof. Okay, my way of doing it is definitely you can see different from our textbook, and that's totally fine. So I can have 10 people taking the proving the same question, and these 10 people come up with 10 different ways to prove a statement. Okay, and all of them fine, as long as from one step to another step you can show the argument. Okay, why from this step to the next step is true, next step to the next step is true, so on and so forth. Okay, so let me write it down also that proving is not unique. So different people may come up with different argument. Of course, when I say the different people may come up with different argument, I'm talking about the body. Okay, the green part that I show you here, the body may be different. Okay, the body of the proofing may be different, but the first step, the blue one, and the last step, the blue one here, has to be the same. Okay. Now, of course, that's only first example to introduce you with how to do proofing. Let's do more. Let's do more. I pick question from 5.2. Would you like to pick any questions from that 5.2? 5.2 on page 348. Page 348. What question you want me to do from there?
Um, 58.
58, okay. Number 58. Maybe one more? Okay, we worry about that later then. So we want to prove cosine squared 2 theta minus sine squared 2 theta equals to 2 cosine squared 2 theta minus 1. Now, as much as it looks so scary, the 2 theta is actually the same for each one of them. Right? So you can just see that as cosine squared x minus sine squared x equals to 2 cosine squared x minus 1. Okay, now let's prove this. Now the proof, I will prove that from left to right. Now that's usually the common situation though. Okay, I will prove from left to right. And my left hand side is cosine squared 2 theta, cosine squared 2 theta minus sine squared 2 theta should be equal to that. Now then from here, think about one identity that you can use to prove the right hand side to the right hand side. Now, for example, one thing I know is that sine squared theta is 1 minus cosine squared 2 theta. Right? So the change actually from here to here. And then I go on further. This is cosine squared 2 theta minus 1 plus cosine squared 2 theta. Combine like terms. Right? So I get 2 cosine squared 2 theta minus 1. Oops, that's what we see on the right hand side. Okay. Now, of course, you may wonder about one thing. While you are, I expect you to copy this down. You may wonder, Thomas, why do you change the sine squared 2 theta and not cosine squared 2 theta? Why don't you change this cosine squared 2 theta? Well, because when I look at the terminal, the expression that I try to make it equal to, I already have cosine squared theta, cosine squared 2 theta, right? I just need the 2. Then how do I get that? Maybe I can get it from the sine squared theta. Okay, now that's one way to prove it. I said earlier that we have more than one way to prove it, right? Okay, so let's see another way to do it. Somebody may say, you know what, Thomas? I will write it this way. Cosine squared 2 theta, that's the original one I have. Okay, and I will add cosine squared 2 theta minus cosine squared 2 theta minus sine squared 2 theta. In other words, I add and subtract the same expression. I add and subtract by 0, right? I add by cosine squared 2 theta, and at the same time I subtract that. So I basically add 0. Now, and then I will combine these two terms here and combine these two terms. So I get 2 cosine squared 2 theta minus cosine squared 2 theta plus sine squared 2 theta. I basically factor the negative out, so I get 2 cosine squared 2 theta minus 1. Okay, so you see that proofing is not unique. My first line and my last line are the same, but my body of the proof may be very different. Okay, different ways to do that though. Now that's for number 58. Can we choose one more question? As ugly as possible. Now, I said earlier that you may consider changing it to sine, cosine when it is complicated. Okay, let's take a look on number 64. But you also need to know that it's not always true though. It's not always true. In other words, you can always do that, but you don't always need to do that. Okay, so proof number 64, 1 minus sine squared theta times 1 plus tangent squared theta equals to 1. Now, the proof, I think the shorter one will be as the following. Left-hand side, I have 1 minus sine squared theta. On the right-hand side, times 1 plus tangent squared theta. Now, of course, if you really don't know, you can use change the tangent square into sine square over cosine square. But if you happen to know that this guy is equal to what?
Cosine.
Almost right.
Cosine squared theta.
That's right. That's cosine squared theta. And how about the blue part? That's secant squared theta. Right? That's basic identity formula 2, the first one and the second one. Okay, and then I go on further. Secant squared theta is 1 over cosine squared theta. So the product is 1, which is what we have on the right hand side. Okay, so the more identity you remember, the better. Now, otherwise, then you have to do it long way. Then you need to do it like, for example, this is 1 minus sine squared theta times 1 plus sine squared theta over cosine squared theta. And then you need to do the FOIL 1 plus sine squared theta over cosine squared theta minus sine squared theta minus sine to the 4th theta over cosine squared theta. Well, that's a lot of work there. Okay, and then from here you do the LCD, right? You do the LCD and so on and so forth. That will be very busy. and overwhelming.
If we use a basic identity, do we need to put in which basic identity it is in the proof?
No need, no need. You don't need to write it, but as so you don't need to write this. Is it what you asked? You don't need to write this.
Yeah, that's what I was asking.
Yeah, so you don't need to write that. I mean, I get used to it already, right? I need you to memorize that we have such formula. You don't need to remember the address, even though that would be better. Okay, but you don't need to write it down.
Okay.
But each step you only use one or at most two identities. Okay, so you see that if you don't memorize those identities, you will be very, very busy here for those simple things. Okay, the reason we proved those basic identities earlier so that we can use them conveniently instead of you proving them again. Okay, now that's for 5.2. Let me go on to 5.3. We have proving also there. As I remember that specifically for negative angle. So from section 5.3, section 5.3, take a look on between number 21 to number 26. Tell me which question you want me to go over. This is on page 364. Tell me which question you want me to go over. Number 26 maybe?
Yeah, let's do 26.
Number 26. Proof, yeah, whatever ugly, right? Cotangent negative x times cosine of negative x plus sine of negative x equals to negative cosecant x. I will start from left to right. Okay, I guess I will do it in cosine negative x over sine negative x, cosine negative x plus sine negative x. That's what I do first. So I change that cotangent negative angle becomes cosine over sine of negative angle. Now, what do you think I will do next? Use formula in identity in B4, the negative angles formula, where cosine negative is cosine positive, sine negative is negative sine, like that. Okay. Now then, let me do LCD. So I have cosine squared x over negative sine x equals to, I multiply this by sine x over sine x. So I get minus sine squared x over sine x. Right? That's equals to negative of, I factor the negative, so on the top I get cosine squared x plus sine squared x over sine x. That is negative 1 over sine x. That's negative cosecant x. That's our right hand side. That's the end of the proof. Now notice that when I put my box, I try to put my box in a way that the bottom of that box is in line with the last line, and the right hand side of that box is in line with the rightmost position. I hope you see that. Okay. You can also see here that my box. Okay. Now you don't have to be super precise that it has to be precisely like that, but definitely you don't put it here. You don't put it here. No, 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 no. Okay, you don't put it here. Okay, you don't put it there. Yeah, you put it somewhere around here. Okay, at the basically this box kind of like give the bottom border and the right hand side border. Okay, you will see that even in your calculus textbook they have that kind of notation. Okay, now that's for 5.3. I wonder if 5.4 has that proofing. No, let's jump to 6.1. I jump to 6.1, verifying trig identities. So let me ask you to take a look on section 6.1, page 421. Pick 3 or 4 questions from there. Number 30 is one of them. What do you want, by the way?
I'm okay with doing any of these. Number 30 is good. We can do like an easier one from the earlier problems.
Okay.
Maybe like number 4.
Number 4. Okay, number 4. Maybe one more.
And then
Number 13, maybe.
Number 13. Okay,
Yeah.
number 13. Yeah, we can have more later. Okay, let's do number 4 first.
Mm.
Number 4, we have proof. Tangent t plus 2 cosine t cosecant t equals to secant t cosecant t plus cotangent t. Now let me ask you to write the first line or maybe with the second line too. Something not really right with my laptop. It's my screen. I think I will prove from the left hand side. Okay. So left hand side we have tangent t plus 2 cosine t cosecant t. There are too many functions here, so let me make it into sine cosine thingy. Sine t over cosine t plus 2 times cosine t times 1 over sine t. That's sine t over cosine t plus 2 cosine t over sine t. What do you have in mind? Actually, give me a second. Do you notice that I already have this cotangent t, one of the cotangent t here? Do you see that? Our problem is that too, right? Okay, so I think what I will do is I will separate this. I will separate these two here. I will separate that. So sine t over cosine t plus cosine t over sine t plus cosine t over sine t. Now, then you will see that this cotangent is something I will get from here later on. You see? Right? So I expect this part here will come from the combination of these two. You see what I mean? Okay, let's go on. Let's go on. Then I will do LCD for those, huh? The LCD will be, this is cotangent here. The LCD is sine t cosine t. On the top that will be sine squared t. And here will be sine t cosine t. On the top will be cosine squared t. And put them together, that will be what do I have on the top?
1.
That will be 1. Okay. If you happen to see that 1, you can. I think it's quite reasonable for you to just write 1 there. But if you don't, then I will write it that way first. Okay. So yes, that will be 1 over sine t cosine t plus cotangent t. Okay. Well, secant cosecant. Oh, then I will write that as 1 over cosine t times 1 over sine t plus cotangent t. That's secant t cosecant t plus cotangent t. That's what we have on the right hand side. Oh, this proof is quite long, huh? I don't expect it from number 4. Yeah, but I think the key step is really doing the LCD and take one of the cosine over sine away to help with that, to help with this. And then for this one. Okay, that's for number 4. What's the other one? Number 13, as I remember. Number 13. Prove that cosecant to the 4th t, cosecant to the 4th t minus cotangent to the 4th t equals to cosecant squared t plus cotangent squared t. Oh, number 13, in my opinion, is a lot easier compared to number 4. Yeah, so I will prove from the left-hand side. This is cosecant to the 4t minus cotangent to the 4t. Any idea? I will use difference of squares. Okay, x squared minus y squared equals to x plus y, x minus y. I will use that. Okay, in this case, this is cosecant squared being squared minus cotangent squared being squared. Let me write it. This is cosecant squared t plus cotangent squared t times cosecant squared t minus cotangent squared t. Do you see what I mean? Now then I wonder if you know what is this equal to. B 2, 3. 1 plus cotangent squared theta equals to cosecant squared theta. Right? So if you subtract by cotangent squared theta, it will be 1. Okay, so 1 equals to 1 equals to cosecant squared theta minus cotangent squared. Okay, that's equals to 1. And then voila, that's the right hand side. That's the end. That one happens to be simple. Number 30. So you see number 13 actually based on factoring difference of squares. Okay. Number 30 actually depends on factoring. Number 30, proof cosine cube x plus or minus sine cube x over cosine x minus sine x equals to 1 plus sine x cosine x. Now, things that you have to memorize is difference of cubes. X cubed minus y cubed is equal to x minus y times x squared plus xy plus y squared. Okay, that's what we will use. That's what we will use. So, from left hand side, cosine cube x minus sine cube x over sine cosine x minus sine x. So you use the factoring. What do you get on the top?
You get cosine x minus cosine, oh sorry, cosine x minus sine x,
That's the first factor, that's right.
parentheses, and then cosine squared x plus cosine x sine x
Okay, great.
plus sine squared x.
That's right. Okay, so you notice that this guy cancels with the denominator, right? So we get cosine squared x plus cosine x sine x plus sine squared x. And then what next? Notice that this guy, this guy give you what? Cosine squared x plus sine squared x give you
1.
1 plus, now then I will reorder this here just to make Thomas happy because it's supposed to be sine x cosine x. Now what justify us to reverse the multiplication here? Why is cosine sine equals to sine cosine? Oh, you need to remember that. Commutative property. Okay, commutative property. If you multiply two factors, then it's different order give you the same result, the same product. Okay, now that's for number 30. Now I'm about to, let me give you a break. In between, I would like you to think about question number 9. Maybe question number 7 first. Question number 7. They use 3t, let's just use x. So proof, I modified the question a little bit so that you don't need to worry about the 3t. 1 plus cosine x over sine x plus sine x over 1 plus cosine x equals to 2 cosecant x. Okay, so it's not about the 3t, it's about what this expression, the identity be. Now the hint will be find LCD on the left hand side. Start from left to right. Okay, you will do from left to right and then do LCD. Now what is the LCD here? On the left hand side. The LCD will be sine x times 1 plus cosine x. Together with your break, that should take you around 5 minutes. Together with your break, we come back at 11:15. So from left hand side, I told you, and we do LCD. Okay, so on the top here, we will get 1 plus cosine x times another 1 plus cosine x. And the guy here will be sine squared x. And then let me put them together first. So I get sine x times 1 plus cosine x. That will be, let me FOIL this at the same time then. I'll FOIL this at the same time. That would be 1 plus 2 cosine x plus cosine squared x plus sine squared x, right? And then notice that the last two terms becomes 1, okay? Together with this guy, together with this guy here, that becomes 2. So 2 plus 2 cosine x over sine x times 1 plus cosine x. Now, what do you think I should do here? Factor 2, right? And you see something cancel with the bottom. So now we get this cancel, this cancel with this, okay, such that I get 2 cosecant x now, which is what we have on the right hand side. Okay. By the way, that's the first method. That's method 1. I want to show you another method. Significantly different method. And in my opinion, it's actually quite a technique that I want to show you. Okay, another way to do that is, what did I do? Why is suddenly so big? What did I do? Okay. Yeah, I want to do it another way. Okay, I want to do it another way. Prove this, the same expression here, number what? Number 7. But I used another method. Now, that's because I know the following. I see that this guy here, okay, that actually stands for 1 over sine x already, right? Which I already see here, right? Okay, so this is what I will do. I will multiply this guy, only this part here, by the conjugate. Only multiply that part by the conjugate. Oh, Thomas, what do you mean by just the conjugate? Here's the situation. So let's see. Let me write the left-hand side first. That's 1 plus cosine x over sine x plus sine x over 1 plus 1 plus cosine x. Now, what I meant is I will only deal with the second term here, okay, and I will multiply by the conjugate. 1 minus cosine x over 1 minus cosine x. Only the second term, So the first term stays the same, 1 plus cosine x over sine x plus the second term will be sine x times 1 minus cosine x. Now, the reason we multiply by the conjugate, is because if you multiply by the conjugate, you will get 1 minus cosine squared, difference of square, right? That becomes 1 minus cosine squared x. Do you see that? Now then, if I go on further, then the denominator for the second term, the second fraction will be, what's the denominator be? That will be sine squared x, okay? Then you see one of the sine cancel, right? One of the sine cancel. Then I get 1 plus cosine x over sine x plus 1 minus cosine x over sine x. Now they already have LCD. Okay, so the first method I did is when I did the first method earlier, I was not aware that I can play with the second denominator and somehow get the first denominator. I didn't think that way. Okay, now, but if you happen to see that it is possibly done, then you show the work, of course, and why they're the same. Okay, now then I can, once they have LCD, I can put them together. 1 plus cosine x plus 1 minus cosine x, which will be 2 on the top. 2 over sine x, that's 2 times cosecant x, that's our right hand side. Okay. I think all the technique that you need, I already show you here. Of course, it still need some creativity and memorizing the formulas. On the top of that, you need to memorize, you need to know how to do FOIL, and you need to know how to do factoring, difference of squares, sum of squares, difference of squares, difference of cube, sum of cubes. Okay, now suggested homework from this 6-1 will be from let's just do from number 5 to number 49. Okay, just do the odd ones. In fact, if I were you, I will do every other odd. Do every other odd first, and then if you have more time, study for your tests and do the odd ones. Okay, just have a feeling, especially on this. Okay, let me go on to 5.5. Let me go on to 5.5. 5.5 is on graphing sine and cosine function. Graphing sine and cosine function. Now, let me ask you to do the following first. Let me ask you to do this. We will first graph the function y equals to sine x. Okay. Now, but for that, I would like you to help me. Do me a favor. I would like you to compute the decimal value for special angles. Okay, for x equals to 0 degree, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and on. And just round it to 1 decimal place. Okay, so after that is 120, 135, 150 degrees, 180 degrees, 210 degrees, 225 degrees, 240 degrees, 270 degrees, 300 degrees, 315 degrees, 330 degrees. Okay, for example, sine 0 degrees 0, sine 30 degrees 0, 0.5, sine 45 degree, I think is 0.71. Use your calculator. Okay, and then sine 60 degrees 0.86, 0.87. This is 1. And then you don't need to actually, if you think about it, you don't need to use calculator anymore here, because for us to find sine 120 degrees, that's quadrant rule, right? So that's positive for sine, and reference angle is 60 degrees, right? Okay, so this is 0.87. With the same technique, you will get 0.71, 0.5, 0, and then negative 0.5, negative 0.71, negative 0.87, 1, negative 0.87, negative 0.71, negative 0.5. Okay, now you may want to copy that down first. Yeah, we'll graph this sine function on this graph here. Let me enlarge that. Okay. This could be the first time you actually graph sine function, and I hope you can mimic that for your cosine later on. But try to follow me. I wonder if I post this in my previous discussion, something like this that I asked you to print out. Okay, but the graph of sine function will be as the following. Notice that the sine function, let me use red color instead. The center is 0. The amplitude is 1. Okay, basically the graph later on will look like this. I give you the sketch only for now. Okay, it will look like this. It will look like this approximately. Okay, that's approximately what it looks like, which means it's the center, I call the center is 0. The center is 0. And the graph goes up and down. The graph goes up and down at most 1 up to positive 1 and go down to negative 1. Okay, so you will see the center is 0. The amplitude is 1. Now, the sine function make one full cycle at 360 degrees. Let's plot this first. Let's plot this first. Okay, so if this is 0 degrees, this is 30 degrees, 45 degrees, 60 degrees, 90 degrees. then it will be 0, 1/2, because you see that there are 5 ticks here to get 1. So this is 0 0.2, 0 0.4, 0 0.6, 0 0.8 if I draw it in, in scale. And sine 45 degrees is 0 0.71 approximately here. Sine 60 degrees, 0 0.87 approximately here. This one is 71, so it's a bit high here. And then this is 0 0.87, right? 0 0.87, and then 90 degrees here. So in the first quadrant, the graph will be approximately something looks like this. Okay, let me make it bigger. Approximately something like this. And then if I go on further, 100. So this is my 90 degrees. 90 degrees, 180 degrees, 270 degrees. Okay, so 120 degrees here, 135 degrees, 150 degrees, and then 180 degrees. Symmetric, very similar. It's here, it's here, it's here, it's here. And we'll make it so. That's for the second quadrant. For the third quadrant, it will be 210 degrees, 225, 240 degrees, and the quadrantal angle 270 degrees. That will be the negative part. If you have a chance, please, at home, try to sketch this also. Okay, at least have a good feeling about the sine graph. Okay, that's what the sine graph looks like. If I summarize, this is 300 degrees here, 315 degrees, 330 degrees, 360 degrees. Or of course, you can also write it in radian. This is 0, pi over 6, pi over 4, pi over 3, pi over 2, this is pi, 3 pi over 2, that's 2 pi. But what I need you to memorize is from that graph, I would like you to see that for y equals to sine x, the center is 0. The amplitude, amplitude represents how far you go up and down from the center. So the amplitude is 1. Now from there you see that the maximum will be the center plus the amplitude. The minimum will be the center minus the amplitude. Okay, so from center with amplitude, then we get the range of sine function. The range will be from -1 to 1. the period is 2 pi, which means the graph will repeat itself every 2 pi. Okay, now then, suppose, for example, using that sine graph, I say graph y equals to 4 minus 3 sine x. Notice that this 4 means up 4. And then this 3 here, vertical stretch by 3 times. And this negative here is flipped with respect to x-axis. Okay, now instead of graphing that this so nice here, instead of graphing it this nice way, I will summarize what we do later into what I call 4 by 2 columns. So these 4 columns here. So this is the two rows, 4 columns. Okay, we'll summarize that into 4 by 2. So then, in this situation here, suppose I have that 4 by 2. So this is the 2 rows. This is the 4 columns. Okay, what's the center?
Four.
Center will be 4. What is the amplitude?
Three.
It will be 3. Okay, so from there we see that the maximum is 4 plus 3, which is 7. The minimum is 4 minus 3, which is 1. Okay, so here the center is 4, the maximum is 7, the minimum is 1. Okay, and there is no change in the period. The period is still 2 pi. And it will follow the graph of sine, except that it will follow the graph of sine, except that we have to flip it, right? So the graph later on will look like this. You know what? Let me write this first. This is 0 pi over 2 pi, 3 pi over 2, and 2 pi. Okay, and the graph will be upside down, it's called upside down sine. It will look like this. Approximately like that. Okay, of course, the actual graph is actually, you keep on repeating that. Okay, you keep on repeating this pattern. Okay, but I will just write it in one period, and that one period looks like this. Okay, now third one. What happened if I have some y equals to 4 minus 3 sine 2x. So basically continue from example 2. The new difference is the period. Notice that this means we shrink horizontally by factor of 2. Now, the consequence is the period. The consequence is the period, which originally 2 pi, now becomes divided by 2. Okay, the period originally is 2 pi. When you divide by 2, now the period becomes just pi. Okay, so and you will see the one change will be the x component here, because the center, the magnitude, the amplitude, the center is still the same. The center is still 4. Okay, the amplitude is still 3. So the maximum and minimum still the same. The range still from 1 to 7. Okay. The period is the one change. The period is now originally 2 pi, but because you play the movie twice faster, it finish in pi units. Okay, so I start from 0, but I finish at pi. That's the difference. Okay, now then here will be this position here will be the midpoint of 0 and pi, which will be pi over 2. This is pi over 4. This is 3 pi over 4. Now, if the graph of sine looks like that, if the graph of sine looks like this, now what will the graph of cosine look like? Let me copy this. So it's very similar anyway. Copy this, bring it down. Okay, and I will delete the sine graph. You will see, using the same technique I showed you earlier, the graph of cosine. The graph of cosine will be actually very similar though. Very similar, but I will start from here. The graph of cosine will be So very similar to the graph of sine, except that it starts from the top. Okay, except that it starts from the top, going to the bottom, and goes back to the top. Okay, now this will be the graph of cosine. Now again, like what I said earlier, I will not ask you to graph that in full. Of course, you need to remember the shape though. Okay, but then what happened if, then from there, you see that the graph for cosine, the center is 1. I'm sorry, center is 0. The amplitude is 1. The period is 2 pi. Okay. Actually, if you think about it, it's exactly the same information to what we have for sine. The center is 0, the amplitude is 1, the period is 2 pi. Okay. Exactly the same. It's just the starting point is different. Now then, what do we do if we have example 4, when I say graph y equals to, let's say 3 minus 4 cosine 3x. Maybe make it 2x instead of 3x. 2x. Now let me ask you to find out from there, find the center, the amplitude, and therefore from there get the range and the period. Okay, later on we will put that into this 2 by 4. The center is
3.
3. The amplitude is
4. -4.
okay. How about the range then?
-1 to 7.
-1 to 7, right?
Yeah.
Okay, and the period will be 2 pi over 2. Okay, we always divide by the coefficient of the angle, and the period will be pi here. So the center is 3, up 4 give me 7, down 4 give me -1. Starting point is starting is 0, the period is pi. Do I start from the top, middle, bottom?
The bottom.
Yeah, start from the bottom because we flip that, right? Okay, because we flip that with respect to the x-axis. So I will start from the bottom, going this way, then going up, this way. Okay, the graph is approximately like that. Okay, now please don't make it too straight though. Please don't make it too straight. It's supposed to curve a little bit. Okay, so it's supposed to curve a little bit. Don't make it straight like don't make it straight like this, like that. No, don't do that. Okay, it's curving. It's curving. Okay. Now then, what happens if we have something called phase shift? Example 6. Suppose I have y equals to, let's say, 4 plus 5 cosine pi, maybe. Oh, don't use pi. Cosine 3x plus pi over 2. Now we will have phase shift here, but before we see the phase shift, factor this 3 out first. Okay, I will factor this 3 out. So 4 plus 5 cosine 3 times x plus 1. If you factor the 3 out, if you factor the 3 out, what do you get left inside?
Pi over 6.
Over 6. Okay, now then from there we see, oh, the center is
Center is 4.
okay. How about the amplitude?
5.
5. Okay, the period will be 2 pi over 3, the coefficient of the angle, and then the phase shift is negative pi over 6. It follows the transformation we learned long time ago. Basically, it moves. This means it moves pi over 6 to the left. Move pi over 6 to the left. And that's why we use negative sign there, because it's to the left. Okay. Now, then what will the 4x2 table look like? Let me make it a bit big this time. The center is 4, the amplitude is 5. So up 5 give me 9, down 5 give me negative 1. Now the phase shift make the x component, instead of starting from 0, you start from negative pi over 6. Okay, not from 0. Not 0. And because the period is 2 pi over 3, it means from here to here, the distance is 2 pi over 3. Okay, so what will the value be here? That will be negative pi over 6 plus 2 pi over 3. Okay, I think you will get pi over 2. Is that right? Yeah. 3 pi over 6, that's pi over 2. Okay, so and then this guy here is the midpoint of this guy and this guy. It's the midpoint. So use midpoint formula. If you use midpoint formula, I believe you will get pi over 6. Pi over 2 minus pi over 6 divided by 2. That's 2 pi over 6 divided by 2 give me pi over 6. Right? Okay. Now, and then this guy here will be the midpoint of these two. But they are opposite, so this will be 0. I think this will be the this will be the midpoint of this guy and this guy. Okay, so I believe that will be pi over 6. 2 pi over 6, so pi over 3, my bad. Okay, so that's the frame. Now, this is the graph of cosine. So where do I start? From the top or middle or bottom?
The top.
From the top. Boom. 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 Okay, now it's a time cut, but suggested homework from 5.5. Suggested homework from 5.5 will be number 1. You don't need to do all of them though, okay? Number 1, I think, and then go on with number 5. I think to number 35 should be good enough. Maybe number 31. Yeah, up to number 31 is good enough. The problem with the problems you have in this 5.5 is that the center is always 0. The center is always 0. If you pay attention, so be aware with that difference between what I taught you before, where the center not necessarily 0. Okay, notice that my center here is 4, right? Now our textbook only deal with, for example, this type. That's what our textbook deal with. Okay, but I believe you can do that kind of adjustment this year. Okay, then that's where I will stop.
Professor, can you go down a little bit? Oh yeah, thank you. Great. Thank you, Professor.